Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh, and very good morning to everyone. Today we are going to continue our lectures with the introduction to unit of concentration. In this lecture, we are going to discuss about introduction to unit of concentration. In the previous lecture, we knew that analytical chemistry deals with measurement. As a chemist, we should be able to express the result we measured in several ways. Before we discuss further about the several ways to calculate or to measure the concentration, first of all, you should know what is concentration and how to choose the most suitable instrument for the measurement in the chemical analysis. Before we start choosing the most suitable instrument for the measurement, we should know what is the level of analyte present in that particular sample. In the instrumental analysis, to determine the concentrations of analyte in the sample, you should prepare a series of working standard solution to construct a calibration curve before you start measuring or you start determining the concentrations of analyte in the sample. In the preparations of the standard solution, of course, you deal with the concentration. At that stage, you need to know how to convert the same concentrations of acid to molarity, for example. In the previous lecture, we have already learned about the types of chemical analysis, which is qualitative analysis and quantitative analysis. And when we talk about the quantitative analysis, we should know how to classify the quantitative analysis either by looking at the level of analyte in the sample or by looking at the sample size. So today we are going to learn how to express the result we measure in a chemical analysis. What is concentration? Concentration can be defined as the quantity of analyte in gram or moles per unit amount of sample, whether in gram or liter. So that means we focus on the measurement of analyte in solid and concentration in solution by calculating mass. So the unit that we calculate mass either in gram or moles. So the quantity of analyte can be measured in gram or moles, and the amount of sample can be measured in gram or liter depending on the state of matter. Meaning that if, let's say, your sample is liquid, then you measure in liter, whereas if your sample is a solid, for example soil sample, then you measure the mass in gram as a unit of the mass. Okay, so quantitative analysis involve identifications and quantifications of the particular. For example, the concentrations of mercury can be measured in part per million. Mercury, for example, here is present in seawater at very low level, at 3 times 10 to the minus 5 part per million. That means it's very, very low. So in chemical analysis, lower level of measurement require more sensitive instrument to determine the concentrations of analyte in the sample. So in this case, you cannot use a spot test to identify it. Of course, you need a very sensitive instrument, for instance, ICP. ICP is stand for the inductively coupled plasma, which is preferred rather than AAS, atomic absorption spectrometry. Because why? Because this instrument is more sensitive. So ICP can detect the level of mercury at ppb level, up to ppb level, whereas AAS only can measure the concentrations of the metal at ppm level. In this slide, this is the result of AAS as a raw data based on the metal analysis. You can see here in this result, the value of the sample concentrations is minus 0.742, minus 0.751. So this is in triplicate measurement. So you can see the result is almost minus 0.7. So if let's say your result you get a negative value, so how are you going to writing up your report? If your result of a quantitative analysis is negative, it doesn't mean that the concentrations of analyte was not identified or detected. Perhaps your method that you use is not suitable, or the instrument that you use is not sensitive enough to detect that particular analyte in that particular sample. So it does not mean that the sample is absent. So it merely implies that the substance is present at the level below that at which the spot test or analysis scheme. Perhaps if let's say you prepare the sample using other method and use the more sensitive instrument, perhaps the result that you get is not negative. So when you want to report your result, in this case, you are actually not reporting as 0, but you need to indicate that your result that you get not detected, or you just use the symbol ND. Okay, I have already said several times that analytical chemistry deal with measurement of solid and solution concentrations of them, from which we calculate masses. What does it mean by this statement? If you read properly, it says that analytical chemistry deal with measurement of solid. What does it mean by measurement of solid? So that means this is a solid that you want to measure. This is the reagent, normally standard of EDTA, as a standard solution that you want to prepare. In this case, for example, so EDTA is the analytical grade analytical reagent that you want to prepare here. So this solid, you calculate the mass by using the analytical balance, and that measure exactly the mass of this solid. So this is the solute. So after you dissolve it in a solvent, in this case water, then you get a solution. So this lecture actually try to teach you how to measure the concentrations of the solution that you prepare from this solid. So this is the concentration that you want to measure. So thus we prepare solution of known concentration that can be used to calibrate the instrument and also to titrate sample solution in the titrimetry. So these are two different techniques that can be used to determine the analyte concentrations in the sample. Okay, if you use the instrumental analysis, then you need to calibrate the instrument by plotting a calibration curve. If you use a conventional technique, titrimetric technique, then normally we have to prepare a standard of solution, and then we use it as a titrant, for example. Okay, so this is what does it mean by this statement. I hope you can understand this. So by referring to the instrumental analysis, in this case, this is one example on preparations of series of standard. This is for the preparations of calibration curve. In this case is GCFID. So the ethanol, this is a standard that they prepare at 4 different concentration here. Actually, it starts with the lowest to the highest. Okay, should be this is the first, second, third, and fourth. And then when you run this standard through the GCFID, then you get this peak. And when you introduce the internal standard, then you get another peak. So when you get a ratio between these two peaks, then you get this value. And then because of each of these working standard is measured in duplicate, then you get 2 different results, and then finally you get the mean for this standard. For each standard you get mean here. Okay, understand that you have 4 points here, 1, 2, 3, and 4. Okay, so this is 4 value. From this value, you are going to calibrate, you are going to plot a calibration curve as shown in the next slide. So you can see here, this is the calibration curve that have already plotted. Okay, and then the R square is 0.99. That means your calibration curve is good. However, try to omit this, because normally the calibration curve should be start at this 0. Okay, so you have to adjust and to make sure that you start with blank or auto 0 the instrument, to make sure that the 0 concentrations of your analyte should get a 0 signal. Okay, this is one example on how to use a standard solution for the construction of your calibration curve in the instrumental analysis. Okay, so the next few slides, actually I want to share with you a study prepared by this student. Actually, this student want to determine the concentrations of the ethanol in the tapai pulut sample. So before she start determining the concentrations of ethanol in that particular sample, she actually tried to investigate what is the most suitable solvent to be used to dissolve ethanol. Okay, so what she did, she chose 3 different solvents. Okay, in this case, she used acetonitrile, acetone, and methanol, and see which of these solvent is the most suitable solvent to be used for the detections of ethanol in the tapai pulut sample. So you can see here in the first slide here, the student used acetonitrile as a solvent, and you can see the acetonitrile peak is the second peak. That means the ethanol peak is appear earlier than the solvent. So this is not good. After that, she repeat with the solvent acetone. So from the solvent acetone, you can see the ethanol also appear earlier than acetone. It means that acetone is also not good to be used as. Finally, she find that the methanol is the most suitable solvent in this case because it appear earlier than ethanol. Okay, so by comparing all these 3 chromatograms, the result indicate that methanol is the most suitable solvent to be used in this study? This is because the solvent peak appear first, followed by ethanol and also this internal standard. Okay, so from the result that are obtained from these three chromatographs, she plot a calibration curve, and then after that she determined the sample with 6 different samples here. So you can see from this sample she can calculate the concentrations of ethanol in percent concentration weight over weight. Alright, so the student here express the result that has been measured in unit percent concentration as weight over weight. Okay, so next we also can use the solution that we prepared to prepare a standard. Okay, for example here this is in the conventional technique tetrametry. In this tetrametry technique, we use this technique to determine the quantity of reagent of known concentration that require to react with the analyte. In this case, you can see here that this is a burette. Normally this is the concentrations of the titrant that you want to determine the concentration. And then in the conical flask, normally this is the primary standard that you have prepared, that we have already know the exact concentrations of this primary standard. From this tetrametry, we can calculate the analyte present in the unknown sample. By referring to the lab manual for experiment number 2, you can see here this is for determinations of bismuth and lead using the tetrametry technique. We can say that the more specific technique is complexometric titration of metal ion. So in this case, you need to pipette 10 ml of the unknown in a conical flask and then add a xylene orine and dilute to 100 ml with the distilled water and use it for the titration this unknown with a standard of EDTA. So this standard EDTA, before will be introduced to this titration, this standard EDTA should be standardized first. So in this case, it will be standardized using the zinc sample standard, primary standard. Okay, so in this case, the primary standard is added in this conical flask. So the zinc, granular zinc that you prepare in a solution form is adding in this conical flask, and then the EDTA actually we add it in the burette as a titrant. So from this volume of the titrant, you can calculate the concentrations of the titrant after we actually knowing this primary standard concentration. In this case is zinc. Okay, so this is the importance of the preparation of standard solution in chemistry. So from this, actually we can calculate the result obtained from the standardization calculation and also from the titration. Before I end my lecture, as an exercise, please try yourself on how to calculate the mass of the sodium chloride present in 0.250 molar of solution. After you try yourself, then compare the result that you get with the answer shown in this slide. With that, thank you for your attention.